plus the net momentum flux. So rate of momentum accumulation is, obviously it's a d by dt. Over the volume. The momentum is actually rho times v dot v. Silly me, I'll actually just look at my notes here. Slightly off here, sorry. So it's rho v dv. That's the time rate of change of momentum inside the control volume due to any unsteady fluctuations. We'll add to this the net momentum flux out of the control volume, and that's actually a surface integral of rho v dot ds, and again the v dot ds is so that we're making sure we're comparing the outflow versus the inflow, and that's integrated, that's multiplied by the velocity vector. So this turns out to be a scalar, it's multiplied by a vector. So these are the two terms that go into the change in momentum versus time, and so when we combine everything, we'll write this all out. This F equals ma, all this one big equation. You have the integral over the volume of the body forces, rho dv, minus integral surface forces, ds. Surface tau ds. And that's equal to the rate of momentum accumulation inside the control volume, rho v dv, plus the net momentum flux out of the control volume. And so this is perfectly fine, again, for the integral form of the equation. If we wanted to derive the time check here, if we wanted to go ahead and get the partial differential form, we can do a similar thing as with the continuity equation. So for the terms that are integrals over the surface, we'll apply the divergence theorem. For these two terms, we will, and actually before we do that, we'll make sure to write this component-wise. It makes it a bit easier, and we'll bring this inside of the integral in order to rearrange this to get the partial differential form of the equation. So let's first this is easy to apply divergence theorem. This one's tricky to apply a divergence theorem without first writing it component-wise. So I'll just I'll start with that term. So I have the integral over s of rho v dot ds times u. Actually gives us a surface integral of rho u. Yes. Over s. And if we apply a divergence theorem then to this, what it gives us is an integral over the volume of grad dot rho uv dv. And so we'll note here that in order to apply the divergence theorem, you take whatever you're integrating over the surface integral and dot it with the gradient symbol, and then integrate that over the volume. So we've applied divergence to this and got it and achieved it in terms of a volume integral. We'll do the same thing for the viscous force, and for now I'll actually just call this, instead of going through the entire divergence theorem, I'll just call this F viscous in the x direction. So the viscous force, the component of the viscous force, and I'll actually make it a lowercase f, the differential component of the viscous force in the x direction. And finally, let's apply the divergence theorem to this term. So instead of the negative integral over a surface, it'll be a negative integral over a volume of grad dot pressure dV. And so now that everything is written in terms of a volume integral, we can, and of course we can move this d by dt into the volume. We can go ahead and combine everything into one big integral. And of course, as we mentioned before, if we move this to the left-hand side of the equation, we would note that the right-hand side is equal to 0. In order for this volume integral to always have the left and right-hand sides equal to each other, it must mean the integrands are equal to one another. So we can essentially get rid of the integral symbol and just write it in partial differential form. And there you have it. That is the conservation of momentum equation in its partial differential equation form. And there you have it. You've completed the question minus the energy equation. You've completed the question minus the energy equation. You need a little more time to do the energy equation in the 15 minutes that you've been allotted. So if you see any mistakes, please point them out. Otherwise, see you next time. Thanks.